Hello. Here we are talking about the concept at material points. We are talking about stresses and strain, and then also the stress components. Today's subject is principal stresses. In 우리말, it is called 주응력. But before we talk about the principal stresses, I'd like to revisit the concept of force vectors and the projection of the force vectors. Okay, let's prepare a new page here for this discussion. Let's imagine that we have a vector in space. Let's say I have this vector. So I want to call this vector is what? F. Okay. So we can consider various kinds of coordinate system to interpret this vector system. The first, I want to consider this coordinate system. So x1 or x2, or according to the textbook notation. So we want to, instead of x1 and x2, we may want to use x and y. And also we want to consider another coordinate system is rather rotated, which is parallel to the direction of the force vector. Here, this I want to call this is so x prime, and then this is y prime. And then the difference in these two different coordinate systems can be measured by angle theta here, isn't it? So now let's try to interpret the physics. Well, let's try to measure this vector with respect to choice of coordinate system. So we can measure this vector f two differently. Sorry. So vector f can be measured with respect to blue coordinate system. Let's change the color here. So fx, and then the normal direction in x direction, and x plus, and then the projection of the vector in the blue coordinate system, the normal in the y direction. And also the same vector can be written differently. So with respect to red coordinate system, the projection of the same vector in x direction, and then this is the normal in x prime direction, and let's say put prime here, x prime, and then f y prime and y prime here. Okay, so make sure that these two expressions are exactly same. So we are talking about the same vector here, but depending on the direction where we observe this vector, then we have different measures, isn't it? So obviously, so if you measure the vector f with respect to blue coordinate system, its projection is what can be measured. Its projection is, this is a projection. This length is equal to fx, isn't it? And then if you project the same vector to the red coordinate system, we have different value. It is very obvious here, isn't it? This is fx prime. And then here, graphically, we can easily understand that the fx prime must be greater than the blue fx1, isn't it? So typically, probably fx prime would be the maximum one, isn't it? Okay. So depending on this observation direction, there exists a certain direction where we have the maximum projection of the force vector. The same principle can be applied to the stress condition. So now let's talk about the stress condition here. Say as a first example, so I want to consider one-dimensional problem. Say I want to consider one-dimensional positive stress state. So it is subjected to a tensile stress component here, so which is measured by norm sigma. And then if you want to introduce this coordinate system here, the x and y, and then this if you measure the stress state from the right hand side, then this is what? So we have certain traction vector. Make sure this is a vector. Its magnitude is equal to sigma, and then its direction is what? Its direction is normal, the nx direction. And then if you look at the same stress state from the left-hand side, if you look at here, this is, I want to say this is a traction on the right-hand side, and then if you measure the same traction on the left-hand side, its magnitude is equal to sigma, which is exactly same as before, because we are talking about the same stress state. And but the direction is opposite, minus nx. This is the characteristics of stress state, isn't it, right? And then I'd like to define the direction where we measure. For example, in the case of first one, we measure the stress state, we consider the projection of stress state with respect to this direction, isn't it? So this is equal to, that direction is equal to nx direction. But here, if you look at the left-hand side, we have what? This is equal to minus nx direction, isn't it? So that's why if you want to look at the stress state here, in the case of the first one, I want to measure the stress state with respect to this direction. Then as a consequence, I'm going to obtain this direction. And then let's check the left hand, what happened on the left hand side. So I want to measure the traction minus nx direction. Now, if you read the stress state, then I get this traction, sigma, and then minus nx. So if you simplify this, I have sigma nx and nx. And how about this? Because I have minus and minus, sigma nx and x. This is what happened. Look. So although we have different traction depending on the observation direction, if you rearrange everything, combining, the direction where we measure the stress state, and then the direction for what we read, then we can get exactly the same result here. Okay. All right. So now let's try to measure the traction here. So this is a stress condition. So I have this stress condition, sigma nx and x. To represent the stress state, we need two directions. And if you want to read the traction, in certain direction, so we need to consider dot products. So if you consider this is equal to 1. This is our traction. Sorry, sigma and x on the right hand side. And then let's do the same for the left hand side. Then instead of this, here we have to plug in minus of nx, because its direction is given by minus nx. Then as a consequence, nx dot product is equal to 1, and then, but I have minus sign, so minus sigma nx. That's how we can read the traction existing on the left hand side for the same stress state. So here we are going to read the traction in various directions. So what's going to happen if you read the traction from here? Okay, let's try to read the same stress state from that direction. Then let's remove this. I want to remove this. This is my stress state. Okay, this is my stress state. And then I want to read the stress state in that direction. So how do you represent its direction? This is given by 0 and 1, isn't it, right? 0 and 1. Then it is given by n and y. Okay, so these two are orthogonal to each other, which means that this is it, the dot product between these two base vectors should be equal to 0. So traction in that direction is equal to 0. So obviously, if you try to read or if you project the stress state in that direction, we have the minimum value of the traction. And if you read the stress state, in the x direction, in this case, then we have the maximum value. So in the concept of principal stresses in 중력, so we'd like to find out the direction where we have the maximum value of the traction, and then we want to find out the magnitude of the traction. That's what we want to discuss regarding the principal stresses. So last time we already discussed how we calculate the stress components in various directions. For example, so we already discussed the stress transformation formula. Sigma theta is equal to the mean stress sigma xx plus sigma yy, and then the stress difference sigma xx minus sigma yy cosine 2 theta, the direction where we observe the normal stress component, and then sine 2 theta. And then the shear stress can be measured by this quantity. And then actually the structure of these equations are almost symmetric. That's why it is very easy to memorize. Okay? Alright, so here we can do the same thing using the vector operation. Let's say I have the stress component sigma xx and tau xy, tau xy. You have to prepare this matrix here, and then let's put the normal, because here look at this. To calculate the traction existing in one certain direction, so we consider dot product, isn't it? So we just consider dot products here, nx and ny. Okay, nx and ny. And then as a consequence, we can get certain traction here, tx and ty, traction component x and y direction. We get what? Sigma xx nx plus tau xy and y, and tau xy and x, and the sigma yy and y. This is traction. Then how do you calculate the normal stress component? Normal stress component in that direction is we need to consider one more dot product. So we need to consider one more dot product. Then sigma theta should be equal to traction and the dot product normal. So we need to consider one more dot product. Then nx sigma xx and x plus tau xy and y plus ny tau xy and x plus sigma yy and y. So even without memorizing the stress transformation equation, we can calculate the normal stress component using the concept of the projection of the stress state in certain direction. Then how do you calculate the shear stress component? The calculation of shear stress component is also very easy. Then how? Once we calculate this normal stress component, you just subtract the normal stress component from the magnitude of the traction using Pythagorean theorem. Then you can calculate tau theta without memorizing this equation. Please keep in mind the concepts, the relation between these different concepts. Okay, here then when we have the maximum traction value, the maximum traction value can be obtained with, let's say, in different directions. So we have normal stress component and then shear stress component, and then this is direction, the observation direction, isn't it? And the combination of these two tractions, then it is not aligned with the direction of the plane where we observe the traction. In certain directions, if these two directions are aligned each other, then we're gonna get the maximum, the normal stress value, or the minimum normal stress value, isn't it, right? So in that case, for example, sigma xx and sigma, according to our text notation, so tau xy and tau xy is sigma yy. And then if you want to consider, dot product in certain direction, okay, what I'm talking about a certain direction, then we're gonna get certain traction whose value can be measured by this traction, or I want to use lambda here, lambda, and then each direction of traction is given by this nx and ny, because if the current direction is the principal directions, the direction of the plane is the same as direction of the traction. This is what happened in the principal directions. So that's why if you move, the right hand side to the left hand side, then what happened is we have sigma xx minus lambda tau xy sigma yy minus lambda, and nx and y is equal to 0. So are you familiar with this equation? Yes, this equation is nothing but just eigenvalue equation in engineering mathematics. Eigenvalue problem. So how do you satisfy this quantity? There are two different cases. The first one is if nx and y is equal to 0, then we can satisfy this identity. But in that case, it is trivial, isn't it, right? We are talking about non-zero or the directions. That's why the only way to satisfy this identity condition is the determinant of this matrix should be equal to 0. This is called the singularity condition. By solving this singularity condition, then we can determine the lambda. The lambda is the lambda value. If you solve this, this is a quadratic equation. So we have two different lambda values, isn't it? So that corresponds to maximum and the minimum principal stresses in our in our discussion of stress state. And this is the mathematical background for the principal stresses. You understand? Okay, then how do you extend to three-dimensional configuration? In the extension of this eigenvalue approaches to three-dimensional configuration, let's say you have sigma xx, tau xy, tau xz, and let's say yx, sigma yy, and tau yz, and then tau zx, tau zy, and then sigma zz. And then again, we consider this eigenvalue condition. So nx, ny, nz should be equal to, a traction, but this direction is same as the observation direction. Then we can build, this is lambda. Then we can build another eigenvalue problem. So sigma xx minus lambda tau xy, tau xz, and tau yz, sigma yy minus lambda tau yz, tau zx, tau zy, and the sigma zz minus lambda. Its determinant should be equal to 0. So this is a third order polynomial equation, isn't it? So we have the three different lambda values. They correspond to three-dimensional principal stresses. Is it clear? Okay. So I hope this information is very useful for you guys to understand the concept of principal stresses. And then also we can obtain the principal stresses mathematically using the stress transformation formula. The principal stresses value are nothing but just maximum and the minimum values of the normal stresses. Then we can obtain that values by minimizing or maximizing the normal stress values, isn't it, right? So we have this expression of normal stress from the stress transformation formula, and what we do is we take the derivative, the differentiation with respect to direction of observation direction, and we let this is equal to 0, then we have this equation. So using this equation, so we can obtain the direction of principal directions, and then the information of principal directions is given by this tangent from this equation. Okay. Okay, so if you solve the principal stresses in advance for two-dimensional problem, so we can obtain this closed form solution in two-dimensional cases. So we don't have to worry about the matrix manipulation. But in three dimensions, it's more complicated. So please keep in mind the concept or the relation between the principal stresses and the eigenvalue concepts discussed in engineering mathematics class. Okay, so that's all that I'd like to deliver you to guys to help you guys to understand the concept of principal stresses. Okay, see you next time.